Hello. So to introduce the purpose of this video, the goal of this video is to introduce the underlying idea of the F statistic. So to do that, I'm going to start from the hypothesis testing for a single coefficient, and we will think about how we can extend one-dimensional hypothesis to multiple-dimensional hypothesis. So let's review how we test a single coefficient. So we have beta 1 hat. Suppose that we are interested in beta 1, and beta 1 hat is the estimate from the data, and beta 1, 0 is the value your hypothesis is specifying. So you believe that beta 1 equals to beta 1, 0, but your data tells you that beta 1 equals beta 1 hat. So if they are the same, that means your hypothesis is perfectly consistent with the data. So if there was no estimation error, except for estimation error, it means your hypothesis is correct, looks very much correct. And then when can we reject the null hypothesis? The idea is simple. When those two are different from each other. So, or we measure their difference is different from 0, then the hypothesis is likely to be wrong. So this is the difference is the distance. I will describe this as the distance between your hypothesis and your estimate. And then the distance is standardized by the standard error, and that is the t statistic. So we take difference between hypothesis and the estimate, and then standardize to incorporate the size of the potential error. Potential random error is incorporated into the statistic by the standard error. So the result is the t statistic. We are going to extend this idea to two coefficient case. Nothing is different. So you can think the same thing. So if beta 1 hat equals to beta 1, 0, and beta 2 hat equals to beta 2, 0, that's the case when the hypothesis is correct, other than random error. So if the estimator is correct, then you are going to get these equalities, two equalities at the same time. Then when can we reject it? You need to look at the distance between estimate. Now the estimate is a vector, two-dimensional vector. And the hypothesis is also, the value in the hypothesis is also two-dimensional vector. So you have to think about the distance between your estimate vector and your hypothesis vector. As the distance increases, the hypothesis is more likely to be wrong, right? So idea is the same. We are going to measure the distance. The distance was easily measured by the difference in one dimension, but in two-dimensional, still you can measure. But and then the next step is, so we need to measure the two-dimensional distance, and then we are going to standardize the distance using the standard error, something like the standard error. What is the extension? So we need to think about how we can extend one-dimensional standard error to multiple dimensions. That is another step. So let's first think about the distance. The distance can be easily understood by a picture. So suppose that so it's a two-dimensional plane, beta 1, beta 2. Beta 1 and beta 2 are here and there. And suppose that your estimate is here and your hypothesis is here. So you believe that beta 2 is very small and beta 1 is about here. But after estimating them, you get quite a different values. Beta 1 hat, beta 2 hat are both larger than you expected. So then we are interested in the distance. We have to measure this distance on this two-dimensional plane, which is not a big problem. You know how to do this. By the Pythagoras Theorem, you know the distance can be written in this way. So d1 is the distance in the first parameter, and d2 is the distance in the second parameter. So if you know the distance in the horizontal axis and the vertical axis, then the diagonal line, the length of the diagonal line can be calculated this way, right? Remember, the Pythagoras theorem is about the diagonal length of a triangle. So this is the distance. However, this distance is not standardized. So it does not include, does not tell you how much error can happen or what is the relative size of the distance relative to the size of the random errors. So you may want to, you can now then, let's think about standardization of this guy. The easiest way to standardize the distance is using the respective standard errors. Standard error of beta 1, standard error of beta 2 are divided for the respective differences. So simply this is T1, this is T2. So you may consider this kind of measure, T1 squared plus T2 squared. So T1 and T2 are combined as one distance. It sounds better. It makes more sense statistically than distance without standard error, without considering standard errors. And also, you may think this is a natural extension of one-dimensional hypothesis testing, because so simply you can think that remember that we reject the single hypothesis if T statistic is outside of plus minus 1.96. This is equivalent, this condition outside plus minus 1.96 can be written as this way. So outside plus minus 1.96 so we have to consider plus and minus because it is one-dimensional. There are two sides. However, in this distance, there is no negative sign. Minus, it does not exist. So if you consider the distance in one dimension, it becomes this condition. So extending the same idea, you may interpret this as the distance, and this is the distance. So we are going to reject the joint hypothesis if this distance is greater than something. Something may be different from 1.96. It will be different from 1.96, but conceptually, that is the straightforward extension from one-dimensional procedure. So one-dimensional method was based on the distance, and then the distance can be extended to two-dimension. It is not a big problem. So right, then, by the way, however, this is not complete. The standardization is not complete by this because, so remember, the standard errors are basically their variances. It's related to the variance. But then in the standardization of two-dimensional vector, one important thing that's missing is the covariance. So in estimation of beta 1 and estimation of beta 2, the random errors can be correlated. For example, when beta 1 is overestimated, beta 2 may offset the overestimation by underestimating beta 2. So in that way, they may move together or move in the opposite direction. So the covariance is an important and maybe useful information, but that is not used in the standardization. So therefore, we are going to incorporate covariance in the standardization in this way. This is the complete way of standardizing the two-dimensional distance. So the distance, so this term and this term are the same. These are the same. However, we include a cross product term. Cross term is included, and the cross term is divided by covariance, and 2 is multiplied. Intuition behind it is like think about the expansion of a square. So a1 plus a2 squared is a1 squared, a2 squared plus 2 times cross product. So we are doing the same thing. t1 squared, t2 squared, and t1, so they're cross product, but the denominator uses covariance. So this is inside the radical is a kind of F statistic. This is how we generalize one-dimensional testing method to multiple dimensions. So then in the end, this is the F statistic. So the textbook does not explain how the intuition behind it. So I explained the intuition behind the F statistic using the simple graphs and some simple arguments. And this is the result. Here we have T1 and T2. These are T statistics, and rho is the correlation between those two T statistics. So the rho contains the information about the covariance. So the covariance is captured in here, and some algebra will make F statistic this form. But the idea is simple. So the F statistic does not have the radical, but inside the radical, it can be replaced by this. So then also the idea is the same. So interpretation is the same. The F statistic will be interpreted as the standardized distance between the hypothesis and the estimate. But even though the standardization process is a little more complicated than, quite complicated than one-dimensional case, still the implication is the same. So because F is a distance, if the distance is large, we think that the hypothesis is not consistent with the data, so the hypothesis may be wrong. So we are going to reject when F is too large. That is our approach to the joint hypothesis testing. Okay, we are going to discuss more about the F statistic. It was just intuitive explanation, and I will give you more concrete examples and how we implement F statistic. Okay, see you in the next one.